independent probability evolution. This is basically we are going to discuss one distribution, that is exponential distribution. Actually, we have many distributions: variable distribution, normal distribution, exponential distribution. So, as per our syllabus, before that, now we'll see different types of functions in the system. Types of failures. So basically, these failures are two categories. First one is catastrophic, means permanent. Okay, or also known as permanent failures. And second category is repairable failures. So this category is the permanent failures. Once they are occurring, once they arise in the system, then there is no solution. You cannot repair that component or system once if you have the permanent failure with that particular component or system. Whereas this repairable failures, we can repair them and we can get them back to the normal operating system. Okay. Now again, these repairable failures are divided into two categories, that is based on discrete random variable, random failures, and then these are the next one is continuous. Random failures. So to analyze this discrete random failures, then we'll follow one method or system, that is Markov chains. That is Markov chains. Here to analyze this continuous random failures, here we will follow this system, that is process, that is we will follow this Markov process. Okay. Now here we will discuss regarding various functions and then their relationship, interrelationship between these functions. So what are the various probability functions we have? First one is failure probability density function. As this is the density function, we will always represent with small f of t. And second one is failure probability distribution function. So here, as this is the distribution function, already we have discussed regarding small PDF, capital PDF, like density and distribution functions. So now, as this is the distribution function, this will be represented as capital capital letter, that is capital F of t. And third one is reliability function. That is R of t, capital letter R of t. Fourth one is hazard rate function. What is the hazard meaning? Hazard means that is failure only. Hazard rate function. That is like failure rate function or failure function, that is hazard rate function. It will be represented as small h of t. Now straight away, without going any detailed derivations of each function, I would like to give you the interrelationship between these functions. That we will see. I will give you one table here, so from that you can get clear knowledge on that. Okay, now relationship between all these functions we see. Relationship between these functions, what are those? Small f of t, capital F of t, R of t, and finally h of t. So now I am going to draw one table here, different functions. Okay, now by use of this relationships, now we are going to derive an expression for expected value. There in previous sessions already we have discussed regarding the derivation of expected value and standard deviation using binomial distribution for discrete random variable. But now here we are going to discuss the derivation for expected value using this time dependent probability evaluation, that too using exponential distribution. We'll see it. So already we have the discussion. Already I have discussed regarding the definition of this expected value, that is number of times of occurrences, and its probability density function, yes or no. So now same here also it is implied. Now E of x, expected value, is equal to sigma x is equal to 0 to n x into f of x. Now with respect to failures, now we are deriving this expression, right? So now this equation is for the discrete random variable. Already what we have discussed so far. But now we are dealing with continuous random variable, that is for continuous random variable that is e of t is equal to integral 0 to infinity t into f of t dt, where t is the number of times of occurrence here. Okay, so because as you are in time dependent probability evaluation, then we are dealing with times. Now we are going to simplify this by using the few functions equations. Integral 0 to infinity t into, we know that f of t in terms of capital R of t in the table, above table, d by dt into capital R of t, okay, into dt. Now further simplification, I am writing like this, the above equation, integral 0 to infinity t into this dt gets cancelled now. Now finally this becomes minus d R of t. Okay. Now what I am doing here, I am taking this minus outside of this integral. Now minus integral 0 to infinity t into d R of t. Now if you see the equation, how it looks, see here, this here we have t and d R of t. So now as for the integrals, now we can represent this equation as like this. Now the above equation is, that is, this is in the form of integral t, that is t into d R of t is equal to, like, how it is, like integral u into dv. Integral u into dv. You know that integral u dv equation, that is u into v u into v minus integral v into du. Okay, like this we can write the above equation. Now see how we can write that above equation. Here u is, here u is this t and dv, this dv is this d R of t, where v is R of t. So now above equation again we can write like this, that is e of x, sorry, e of t is equal to minus, as such it will come, minus of minus t R of t, that is uv, okay, minus now integral v dv, that is integral R of t dt. Now already we have the limits 0 to infinity. Now further we are separating them, that is this is not minus already, that is So this is plus only. Now minus t into r of t limits 0 to infinity plus integral 0 to infinity r of t dt. Now we know that limit t tends to infinity r of t is equal to 0, whereas limit t tends to 0 r of t is equal to 1. Okay. So now from this we can write like e of x is equal to, so now this becomes 0 plus integral 0 to infinity r of t dt. Now this is t. Now e of t is equal to integral 0 to infinity r of t dt. This is the remaining finally. Okay. Now this also can be written like mean time to failure. You know that mean time to failure, that is MTTF. Mean time to failure is also representing as small m. Now this E of t is a mean value only, that is expected, that is m is equal to integral 0 to infinity r of t dt. But here, as per the exponential distribution, r of t is equal to e power minus lambda t. Okay, where lambda is the failure constant or hazard rate constant. Failure constant or hazard rate constant. So now we will substitute now this in this equation. Now finally our E of t, small m or E of t is equal to integral 0 to infinity, where r of t is equal to e power minus lambda t into dt as substituted. Now that is equal to, after simplification, then this is e power minus lambda t by minus lambda, that is with the limits 0 to infinity. Taking integral after, we will get this. So now after simplifying this, this is 0 minus of minus 1 by lambda. That is equal to 1 by lambda. Okay, this is E of t. Now from this, what we can say here, what we can conclude here is the expected value of continuous variable is equal to reciprocal of hazard rate constant or failure rate constant, that is lambda. Okay, so this is regarding derivation of expected value using an exponential distribution for continuous variable.